Hello everyone and welcome to lecture. Today we'll be talking about an introduction to trigonometric functions and how trig functions are used to solve problems and how they're used in general in calculus. These functions are very special and very fundamental to many different applications in calculus. So we want to make sure that we understand them well. These functions have many different applications and are essentially used to help us determine a relationship, a geometric relationship between angles and distances in any scenario that you might have to measure the angle or the distance. Specifically, they're based on what's called the unit circle. So I'm going to draw a picture of the unit circle here, and then we're going to kind of talk about how to use this to define the trigonometric functions. So the unit circle is the circle of radius 1. And specifically, we can define the angle from the x-axis as theta, which can be measured in either radians or degrees. That's what we talked about last lecture. So using this unit circle, we can actually directly define exactly what we want in terms of the functions, the two basic trigonometric functions, sine and cosine. Specifically, we say that the x coordinate of the unit circle, of points in the unit circle at a given angle, is given by what's called the function. We say it's cosine of theta. And the y coordinate of the unit circle is given by sine of theta. So this distance right here, from any point down to the x-axis, is given by sine of theta. Now what's nice about this picture is that we have a right triangle here. So this is all based on essentially a right triangle on the unit circle. Remember, the hypotenuse of this right triangle is 1, because it's the unit circle. And then we say that the height is just cosine of theta, and the width of this triangle is cosine of theta, and the height is sine of theta. So that defines exactly what the relationship is for the unit circle. This actually works for any circle of any radii. If we take a copy, maybe of a larger or smaller circle, with a different radius, so maybe something that looks like this. For any angle, we still have this same picture right here. It's that we have a right triangle, and the circle is similar to the circle of radius 1. So even though it's maybe a smaller radius here, a radius of r, we still have that the x coordinate and the y coordinate are related through this right triangle, because these two triangles are similar to one another. So because of that, we still have, say, that the cosine and sine functions are relevant here, in the sense that the relationship that we have is going to be, well, for the unit circle, if x is equal to cosine of r, or cosine of theta, really what we have here is that x over 1 is equal to cosine of theta. And because this triangle is similar to this smaller triangle, same angle theta, the relationship that we have for the smaller circle, or really any other circle of any other radius, is going to be that x over r is equal to cosine of theta. And similarly, you have that y over r is equal to sine of theta. Because for the unit circle, the y over 1 is equal to sine of theta. So because these two triangles are similar to one another, these two right triangles are similar, this is exactly why we have these relationships. So in general, now, for any circle of any radius, y is equal to r times sine theta, and x is equal to r times cosine of theta. And this gives us essentially the basics of all we need to deal with trigonometric functions. The idea is that it's all based on basic geometry and basic essentially similarity of triangles. And these relationships right here, x for a general circle, x equals r cosine theta, and y equals r sine theta, is actually, it's what's called a different coordinate system, the so-called polar coordinates. Because it's giving us the points in the Cartesian plane, so x and y, but it's giving us those Cartesian points in terms of the radius and the angle of a given circle. So there are many different things that we can do and applications that we can do with just sine and cosine, but it turns out that there are also a number of other trig functions that are very, very useful for us. Specifically, we'll talk about this now. So we've seen that for any circle, sine of theta is equal to y over r, and cosine of theta is equal to x over r. We can also define what's called the tangent function, tangent of theta, and this is going to be equal to so it's going to be y over x. So y over r is, we sometimes say that it's the opposite over the hypotenuse. Because if you take this angle theta here and you consider this right triangle, the opposite edge of the angle theta is the side y. So that's why we call sine theta opposite over hypotenuse. Cosine of theta is sometimes called, we say that it's the adjacent edge over the hypotenuse. For the exact same reason, the adjacent edge of this triangle is x right here. It's the adjacent, or the edge adjacent to the angle theta, and divided by the hypotenuse r. And then tan of theta is y over x, or the opposite edge over the adjacent edge. And so these are the three very basic trig functions, and we have three that are slightly more complicated, but are also very, very useful. The first one is called, we call it cosecant. Of theta, which is just 1 over sine of theta, or r over y. If you do 1 over y over r, that will simplify to r over y. We have the function called secant theta, which is 1 over cosine theta, which simplifies to 1 over x over r, or just r over x. And then lastly, we have what's called cotangent of theta, which is 1 over tangent of theta, or x over y. So in terms of the basic trig functions, there you have it. These are the 6 basic trig functions that are very often useful and used a lot in different areas of mathematics. The main use for them is typically to relate angles to geometric quantities. So we could be very very interested in what these functions look like if we try to graph them out, and this can definitively be determined in a very straightforward manner by just looking at how the functions behave with respect to angle on the unit circle. So because these functions are dependent on the angle, we might be interested in exactly what they look like. So in all of the arguments about what the functions look like when you're graphing the function, you're always going to be using the unit circle to get a picture of exactly what the graph of the function looks like with respect to theta. So this right here is a picture of the unit circle. And we'll call it, again, just like before, this angle is theta right here. And remember, for the unit circle, it's the circle of radius 1. And cosine of theta is the x-coordinate of the unit circle. And sine of theta is the y-coordinate of the unit circle. And both of these are at a given angle theta. So if we want to make a graph or a plot of these functions, the functions sine and cosine, we can do this exactly by taking theta from 0 to 2 pi. This axis right here is the theta axis. and then drawing out the function y equals sine of theta. We'll do y equals sine of theta in red, and I'll do y equals cosine theta in blue. So if theta is going from 0 to 2 pi, this corresponds to half of 2 pi, which is pi. This value of theta corresponds to 3 pi over 4. And this value of theta corresponds to just pi over, 3 pi over 2, not 3 pi over 4. So the sine function is the y-coordinate at 0 angle, which is 0. That corresponds to this right here. At pi over 2, the sine function is 1. At pi, the y-coordinate is again 0. At 3 pi over 2, which is this angle right here, the y-coordinate is actually negative 1, so it's down right here. And at 2 pi, is back at the point we started at, the sine function is equal to 0. Now to get other values, intermediate values, you can use either a calculator, or you can use what we know about sine and cosine and triangles specifically, which is that for any triangle we have the Pythagorean theorem. So any right triangle, I should say. So what that means is that if we have a right triangle, this is any right triangle, so this has to be a 90-degree angle right here. And this triangle has a radius of r, an x distance of x, and a y distance of y. At x squared plus y squared has to be equal to r squared. So for the unit circle, when r is equal to 1, that means that x squared plus y squared is equal to 1. And this actually gives us a very nice relationship that we can always use. And I would probably call this relationship that I'm about to write down the most fundamental relationship in all of trigonometry. It's that cosine squared plus sine squared is equal to 1. It's always equal to 1 for any angle, no matter what the angle is. So I'm going to call this the most fundamental trig identity. Because this essentially tells us that the cosine and sine are the x and y coordinate of the unit circle. But using that equation, you can actually use this equation to get sine and cosine and some other we'll get into other trig identities a little bit further down the line. But the main idea here is that, say, if you want to figure out what the sine of pi over 4 is using that identity, Well, pi over 4 is 45 degrees, so it's about this angle right here. This angle right here corresponds to pi over 4. So here theta is pi over 4. And you can see hopefully from the picture that sine is equal to cosine at that point. Or the x coordinate and the y coordinate are the same at that point, because we have it's a 45 degree, 45 degree, 90 degree triangle if you make this triangle a little bit bigger. So what that tells you is that cosine of pi over 4 is in fact equal to sine of pi over 4. And from our fundamental trigonometric identity, we kind of bring this down here. If cosine of sine of pi over 4 is equal to sine of pi over 4, from our fundamental trigonometric identity, that gives us that cosine of pi over 4 squared plus sine of pi over 4 squared has to be equal to 1. Because cosine of pi over 4 squared is equal to sine of pi over 4 squared, this has to be cosine of pi over 4 is the same thing as sine of pi over 4, so this is 2 times sine of pi over 4 is equal to 1 sine squared. So then sine of pi over 4 is equal to 1/2, or sine of pi over 4 squared is equal to 1/2. And what this means is then that you can go through and you can actually solve, and one of the solutions to this equation is that sine of pi over 4, the only solution to this equation is that sine of pi over 4 is equal to 1 over the square root of 2. Which is about right here. And similarly, if you go through, you'll get that another angle which satisfies this is 3 pi over 4. At 3 pi over 4, the sine function is also equal to that value. And then similarly, at the value 5 pi over 4 and 7 pi over 4, the sine function is actually negative 1 over root 2. And I think that these points give us a nice kind of picture of what the sine function looks like in general. It's going to be a curve that comes up like this, and then goes down, back up to 2 pi like this. This is what the sine function looks like for any angle theta. You can do a similar process for the cosine function, in arguing just based on, like I said before, on this unit circle, and you get that the cosine function at 0 is actually 1, because the x coordinate at 0 angle is 1. The cosine function at the angle pi over 4 ends up being the same as the sine function at pi over 4. The cosine function at pi over 2, or 90 degrees, is 0. The cosine function at 3 pi over 4, or this angle right here, is going to be negative 1 over root 2. Cosine function at pi, or at this point right here, is -1. And as we kind of go through and continue this process, we get a nice picture of what the cosine function looks like. Oops. Looks kind of like this. Like this. And then it comes down. Comes back up again. And we can see exactly what the cosine function looks like in relationship to the sine function. So this is a nice plot of both the sine function and the cosine function, and you can verify this using a graphing calculator or some other tool. For instance, if you use Desmos. So let me share the screen so I can show you how to do this using Desmos. So if you were to go to Desmos and you type in sine of x and cosine of x, and remember, these are valid for any values of x, or in our case theta, that you want to plug in, but specifically what we're considering in the plot is the functions over one period, so from 0 here to pi. And you see very clearly that this is exactly what these functions look like. So the idea is that this gives us a nice visualization of the sine and cosine function, and we've also introduced this fundamental trigonometric relationship between sine and cosine. That cosine squared plus sine squared has to always be equal to 1, based on the fact that these functions are defined on the unit circle. So the next function to consider is the tangent function, or what the sine of x or sine of theta over cosine of theta looks like. I'm just going to use Desmos again so that we can kind of see a nice picture. Specifically, we'll do the following. We'll open up Desmos and just plug in tangent of x. And you can see very clearly that the tangent function looks similar to sine and cosine. It's similar in the sense that it's periodic, right? And it matches up directly with what we would expect from these two functions, the sine function and the cosine function. Kind of go here and we look at, say, this value of the tangent function. This value on the tangent function, remember, is sine of x divided by cosine of x. So this value is exactly the red value here divided by the blue value, and this is true at every single given point along this tangent function, the tangent function. Even at this point right here, the tangent function, so at pi over 4, the tangent function is equal to 1 because the values of cosine and sine are equal to one another. So the graph of the tangent function makes a lot of sense. And if you can even consider what the graph of, say, the cosecant and the secant functions all look like as well, and kind of plot them together, and we'll do that right here. So remember, cosecant of x is 1 over cosine, or 1 over sine of x. So 1 divided by sine of x. So that's this purple curve. All of these purple values are 1 over the red values at each of the points. You see that when sine of x is 0, you have the function is not defined. It is an asymptote. Same thing with the tangent function, by the way. Or when cosine of x is 0, when cosine of x is 0, it's this point right here. We have a vertical asymptote in the tangent function because you're trying to take 1, which is the sine function, and divide it by 0 at that point. So we can do secant of x. And then we'll just do lastly cotangent of x. And this plot's getting a little bit full now, so I'll probably take off the individual functions. We'll just first look at sine of x and cosecant of x. So sine of x is here, there's a red curve. And this purple curve is 1 over sine of x, or cosecant of x. And you can see that very clearly that this is behaving exactly how sine behaves. That when sine equals 0 at 2 pi, there's an asymptote of the cosecant function because you're trying to do 1 over 0. Same thing when sine is 0, there's another asymptote of the cosecant function. Similarly, if we look at the cosine function combined with the secant function, you get the same sort of picture. It's the blue curve right here is the cosine function, and the black curve right here is the secant function, or 1 over cosine. So you see very clearly that this function is it has an asymptote whenever cosine is 0. So at this point there's an asymptote. At pi over 2 there's an asymptote because cosine is 0 there. And same thing at any other point where cosine is 0. So in this case at 3 pi over 2 right here, cosine is 0, and there's an asymptote right here of the secant function, because secant is 1 over cosine, which is exactly going to give you 1 over 0 at those points. And so the last comparison function that we have is that the tangent function. A cotangent is 1 over tangent, and you see that it's matching up directly. The tangent function is the green curve right here, and whenever the tangent function is 0, you have an asymptote at the cotangent function because you have 1 over cotangent, and it's behaving exactly as 1 over tangent should. So Desmos is a very good tool for graphing and for seeing these things, but we're going to see a number of different trig identities that help us along in terms of arguing and figuring out things about these trig functions. So the last main example that I want to give you is the following. It's going to be essentially looking at a specific example in physics of where these functions occur. I told you before that there's a number of different really good examples of where these functions, the trig functions, occur, and the main example that I really like to give is what's called damped harmonic motion. So specifically, this example, it has to do with the following. Let's say you have a spring, and that spring is attached to a wall, say, and it's attached to a mass m. And that mass is allowed to rotate back, or not rotate, but oscillate back and forth. So it moves from side to side. And you can also assume that the mass is in maybe some sort of, could be a spring in a car, you know, it could be some sort of brake fluid or other sorts of resistance, but there's some sort of air resistance or maybe even friction as the mass moves back and forth. It oscillates back and forth, left and right, left and right. So using calculus 2 and a little bit of physics, you can go through and show that the position of the mass, if you say that the position of the mass is as a function of time is u of t, well, then it's going to turn out that the position of the mass is going to be given by what's called the amplitude times e to the negative bt times cosine of omega t, where b is a positive quantity that essentially determines how much air resistance there is. Or it's determined by the air resistance. So how much resistance the mass is getting as it's moving back and forth on the spring. And omega is called the frequency of the wave. And what's very neat is that if we kind of look at this, the plot of this function, that this function behaves exactly as you would expect it to. So over time, if this is, we'll say, a plot of the amplitude, or plot of y equals u of t, this function starts when t is 0, at 0 time. And when t is 0, u of t is just equal to a naught. So this distance right here is a naught. And then as time progresses, u of t gets smaller and smaller and smaller, and it behaves similarly to the exponential function and the cosine function. It's like a combination of both of these two functions. And what this means right here is it's saying that u of t, the motion of the pendulum or of the spring back and forth, is oscillatory, but it's kind of getting smaller and smaller and smaller oscillations, or it's being damped. And you can directly see this in Desmos. If you go into Desmos and you open up a plot window and you plot the function, we'll say the amplitude maybe is 2 or 3, and so 3 times, and it'll be e to the, we'll say the damping rate is just 1, so negative t times cosine, and we'll say the frequency is 2 pi. I think it wants me to use x right here. I think that's why I have to use x. Let me... So it's cosine of 2 pi times t. Yeah, so I think Desmos is only going to let me plot with an x right here. But this is fine. We can do that. So here we see exactly what I'm talking about. What this is saying is that if the frequency is 2 pi, then after one period is 2 pi, and you see that the motion, say, with these parameters of b and omega, give us exactly that. It's an oscillating back and forth, but the amplitude of the wave, or the mass, so that the amount of distance that the mass is moving from equilibrium is getting smaller and smaller and smaller as time goes on. And you can see that if we make this a slightly smaller number, like 0.01, so less damping, right? The damping still happens, but it takes a lot more time. Maybe we'll just do 1/2. So it takes more time for the damping to occur. And if you change the frequency, the omega, maybe to just 3, or 3 pi over 2, the actual frequency changes. It stretches out, or it gets more compact, depending on what that value is. But you can see very clearly that this is exactly behaving like we would expect it to. And at 1, the amplitude is just our initial A0, which is 3 in the example. And depending on what the damping rate and the frequency are, we get the exact motion that you would expect from a mass as it sort of vibrates back and forth under damping. So I think this is a really cool example, and serves to kind of be a nice example to show that I can't necessarily show you using calculus how or why this is, because it takes calculus too. But I can at least give this as a nice example of one of the many examples where cosine and sine and the trigonometric functions are very useful. But thank you for tuning into lecture today. I hope you have a great day, and I'll see you next time.